It is available in the trade name Termex, Premise, etc. Very common. It is Termex, Premise, etc. They are extremely effective termiticides. But uh, the problem is it is extremely costly. Yes, usually, normal people doesn't buy it for termite treatment, but uh, those who can afford it can use it. But nowadays, it's picking up well for termite treatment and replacing chlorpyrifos. Okay. So after 1 or 2 weeks, early morning, I had a call from my colleague. He told me that his in-law accidentally consumed this termite water. Last night there was no electricity at their home, so he came to kitchen for drinking water at night. So there was no electricity. There was a bottle of this termiticide. So instead of water bottle at the night, he took the bottle of this imidacloprid SC formulation and drank a bit of it. So he called me up and he told me that morning they realized that he has consumed it. So what could be done? So I told him that according to theory, it should not harm him, but practically we should be careful. So take him to hospital. There shouldn't be any issue. So they took him to hospital. They cleaned his stomach and all. Evening they discharged him. No medicine. So you can see, even if a person try to consume a neonicotinoid, it will not harm him. So that's a kind of selectivity neonicotinoids offer. So this is a personal experience. So this is the kind of selectivity offered by new molecules. So if you trace the history, whenever I discuss about history of insecticides and to UG students, I usually narrate a story. In our rural areas, people used to tell suicides based on the name of insecticides. Earlier, maybe in 70s, when whosoever committed suicide by consuming pesticide, normally the rural folk used to tell that that person consumed paramar. That paramar is nothing but the trade name of parathion, OP poison. Because in 70s, OPs were the major one. Before that, in 16s, whosoever committed consuming pesticide, they used to tell that person has consumed endrin. Endrin was the organochlorine pesticide. In 80s and till about 90s, it was replaced with Firidan. Whosoever committed with whatever pesticide they consume, usually people used to tell that that person consumed Firidan. So that is a carbamate group of pesticides. This shows the evolution of pesticides also in the history. In 60s and all, people were using organochlorine. 70s, they started 70s and early 80s, they were using mainly organophosphates. So those pesticides were easily available. So people use those pesticides for committing suicide. In 90s, they had carbamates in plenty, especially carbofuran. They used mainly carbofuran for committing suicide. But in 2000s, after 2000, in maybe for the last 10 years or so, there is no such common insecticide for committing suicide, because even if a person tries to commit suicide, it's pretty difficult with new generation molecules. So this is how the insecticides evolved. There were pesticides which are extremely toxic, both to insects as well as human beings. But now we have molecules which are selective towards human, not selective towards insect and not toxic to human beings. So let's see how does that work out. Okay, I'll share my PPT. So I given to the title as acetylcholine receptors because we will be discussing about neonicotinoids which act on acetylcholine receptors. So what are the two different kinds of receptors? Nicotinic acetylcholine receptors. Last class we have discussed it. Two different kinds of nicotinic acetylcholine receptors.
MS it is choline.
Nicotinic acetylcholine receptors and muscarinic acetylcholine. NaCH or MaCH. Okay. So this basic things is a primary proteins to which acetylcholine, the neurotransmitter, binds. We have nicotinic and muscarinic acetylcholine receptors. Both differ. Both nicotinic acetylcholine receptors and muscarinic acetylcholine receptors differ. Nicotinic acetylcholine receptors are pentameric that we have discussed, that we have seen the structure. In muscarinic acetylcholine receptor, we have 7 helix protein. And how it differs. Nicotinic acetylcholine receptors are inotropic, whereas muscarinic acetylcholine receptors are metabotropic. Nicotinic acetylcholine receptors are inotropic, whereas muscarinic acetylcholine receptors are metabotropic. I will tell the difference. Inotropic means if it opens, it permits movement of that means if acetylcholine binds to nicotinic acetylcholine receptor, the receptor opens, permits the movement of ions. It can be sodium, it can be potassium, it can be calcium. So that's the 3 species usually nicotinic acetylcholine receptors permit. Whereas metabotropic one, muscarinic acetylcholine receptors, it doesn't permit the movement of ions. It leads to the binding of any ligand to muscarinic acetylcholine receptor leads to metabolic changes. Especially, I don't know whether you have studied it or not, G protein coupled signaling pathways and all. No, it's really there is a signaling pathway other than this neurons which transmits signals. We have signals carried by biological molecules, and one such molecule which is mainly responsible for transmitting these signals is G protein coupled signaling pathway. This is G proteins again. It is a protein molecule which is linked to this metabotropic receptors. So whenever there is a change in the when the metabotropic receptors open, it leads to a change in the G protein coupled pathway, and it leads to a cascade of events. It's not change in electric potential and all. One molecule will generate lead to will transmit a signal to another molecule. One molecule, it's from one point to another point to another, and all this transmission will be mediated by certain biological molecules, mainly proteins. So understand that if you want to have a bit of understanding about G protein coupled signaling, just Google it. You will have innumerable number of material. G protein coupled signaling pathways are there. So this is very common. Try to have an understanding of it, because nowadays people are trying to target this signaling pathway also, because this signaling pathway can also be used for pest management. I don't know whether anyone has evolved any molecule or not, but one thing, this pheromones, pheromones, all those allelochemicals, what we discussed, all these allelochemicals are that initiates a response in insects, isn't it? All these allelochemicals initiates a response, and most of this response is by the way of this G protein coupled pathway. It's not mainly due to this electrical signaling that's happening in neurons. So just have a look at what G protein coupled pathways do. It's a bit energy intensive. That means this G protein coupled pathway requires ATP and all. So read it. I'm not going into deep it because it is itself is another topic. So metabotropic means it's not changes in the electric potential, but it leads to signaling pathways which is coupled to G proteins. Then muscarine, I told you it's a toxin. It's from the mushroom amanita. So this is the structure we have discussed earlier also. It's a pentamer. It allows the movement of sodium, potassium, or calcium ions, either of these three. Uh, it can be one thing you should remember. Here you see it can be heteropentamer or homomeric. That means the nicotinic acetylcholine receptor structure can vary. There are different subtypes of nicotinic acetylcholine receptors. In some organisms, it can be homomeric. That means all the subunits can be the same. While in certain insects, it can be heteromorphous. That means the subunits can differ. So basically, it may be having 2 alpha, beta, gamma, and delta. But among this also, alpha we have 9 subtypes and beta we have 4 subtypes. That means even if an insect is having nicotinic acetylcholine receptor, it can vary, it can be homomer or heteromer. And even in a receptor itself, we can have the alpha subunits, we can have 9 different subtypes of alpha subunit. And if we have a beta take the case of beta subunit, we can have 4 different subtypes of beta subunit. So the diversity of nicotinic acetylcholine receptors is huge in insects. Take one species to another species, even in the same family, from one species to another species, the array of nicotinic acetylcholine receptors is entirely different. So the subtypes, nicotinic acetylcholine receptor subtypes are entirely different in different ones. And all those things, we have 4 transmembrane, all those things we have discussed. M2 forms the 4. And that's the last sentence. That's what I was discussing. The number of binding sites and the affinity of this site to acetylcholine or insecticide differs even within a family. That I will tell. I have not uploaded a paper, but I have a copy of it because that's a bit confusing kind of paper. It's a pretty long paper also, where there are examples of 2 aphids. I think Mysis persicae, that is one aphid, the second one I forgot. And they studied the affinity of this Mysis persicae and the other aphid to neonicotinoids. And they found that for one aphid, we already know that aphids are extremely susceptible to neonicotinoids. But even within this aphididae family, between 2 different species, there is a difference in the number of binding sites, number of receptors for neonicotinoids. I'm just simplifying it. Take one aphid, say Mysis persicae. If it is have 10 receptor locations, 10 receptors in the other aphid will be having only 1. What will happen? Those which are having less receptors will be less susceptible to insecticide. Understood? So that is one. The number of receptors may vary within species, between species, and between different groups of insects. That is one way of achieving selectivity. And another one is, even if the receptors number has also remain the same, say both the efforts are having 10 receptors, the affinity of these receptors to neonicotinoids also vary. Certain insects are having high affinity while certain insects are having low affinity. So this affinity also varies. Let's see how that happens. See, this is the structure of it. Uh, Alpha, two alpha molecules, beta, it's not same, gamma and delta. This is the acetylcholine binding site where this acetylcholine binds. You can see two alpha, beta, gamma, and delta. That's the usual. But even though we tell alpha helix, it can be 9 different types of alpha helix, varying between different species. So if we have different types of alpha helix in different species, this leads to the change in the sensitivity of that insect to neonicotinoids. And beta, we have 4 subunits. If we have difference in beta subunits, it will also alter the susceptibility. This is a typical example. This I have taken from a paper I think I have given to you. Say you can say, don't look into all those things. Look into this part. Sensitivity to alpha bungarotoxin. BGT is a toxin. It is called as bungarotoxin. Bungarotoxin is an extremely poisonous molecule. Bungarotoxin, I forgot it from which organism it is. Let me check. I'll tell just now. Uh, this is from crates, the snake group crate. Have you ever heard of a snake called crate? Crate. So this is a poison from the venom of crate, a poisonous snake found in our country. So this bungarotoxin, how these different nicotinic acetylcholine receptors have their sensitivity to alpha bungarotoxin, extremely poisonous toxic. See, this is the norm, the one, 2 alpha 1 alpha. Here we have seen alpha 1 because they are told to alpha 1 alpha helix we can have 9 subtypes. So here alpha 1 subtype is there, beta is having beta 1 subtype. So 2 alpha 1, beta 1, gamma and delta, the heteromer, it is sensitive to alpha bungarotoxin, a poison. Take this, the next one. This is in the muscle, this is in the nerve. We have, instead of alpha 1, we have alpha 3, alpha 5, and 2 beta. Again, it's a heteromer, but though we have alpha and beta subunits, it is not at all sensitive to bungarotoxin. Takes the next one, again in neuron, we have alpha 4 and beta 2. Alpha 4 is another subtype of alpha, beta 2 is another subtype of beta pleated sheets. Again, it is not sensitive to bungarotoxin. Another one in neuron, another type of nicotinic acetylcholine receptor, we have 1, 2, 3, 4, and 5 alpha. That structure, they are not clear. They are suspecting it to be alpha 7, alpha 8, and alpha 9, the 9 different subtypes. They are homomers. That means all are having alpha helix only. That's why it is homomer. But this is extremely sensitive to bungarotoxin. Now we understood how a nicotinic acetylcholine receptor, we call all of them nicotinic acetylcholine receptor because it is sensitive to nicotine. But we can have different kinds of receptors. It may be constitution varies, different subtypes, alpha we have 9 subtypes, beta we have 4 subtypes, depending upon the varying alpha helices and beta pleated sheet. The susceptibility of or the sensitivity of that particular receptor to toxins vary. Is it clear? Yes or no? Okay. Now you understood how different species differ. Now you can imagine one insect, say a lepidopteran, and another one a hemipteran. Both may be having the same nicotinic acetylcholine receptor. Yes, both are having a nicotinic acetylcholine receptor because they have to conduct nerve impulses. It has to respond to acetylcholine. But one is sensitive, one is not sensitive. Hemipterans are sensitive, lepidopterans are not sensitive. So the difference is that the number of receptors may vary and the binding affinity of the receptors also vary because of the different subtypes of nicotinic acetylcholine receptors. One thing I will add here is that this in the same group, hemipteran group, have you ever studied about a neonicotinoid being used against an heteropteran? Normally, we recommend about homopterans, aphids, whiteflies, mealybugs, scales, etc., hoppers, etc., BPH, etc. But have you ever seen about a heteropteran, neonicotinoid? What is recommended against one of the most common heteropteran? I will tell rice bug, Leptocoryza. What is the normal insecticide recommended against Leptocoryza?
Melaphion.
I, I I didn't hear. You know,
Melaphion.
K is a recommendation of Malathion. What is it in Andhra? Bindu and Swadi? Do you remember? No? So, why still we usually say that neonicotinoids are effective against sucking pest? Then why we are not recommending this imidacloprid against this a sucking pest belonging to the same order Hemiptera leptocoryza? Because heteropterans, the susceptibility is entirely low. It doesn't get killed with imidacloprid. If we increase the dose, yes, it may get killed. But the dose which we normally recommend for aphids, hoppers, etc., it won't get killed. We have a recommendation of imidacloprid against red palm beaver from CPCR, Kasarwood. So there, the recommendation is 1 ml per liter. What is the usual recommendation of neonicotinoid for aphid management or any homopteran management? What's the dose we normally
Point two.
recommend? 0.2, 0.25 to 0.3. Yeah, 0.25 to 0.3. That's the usual recommendation. Here, we are using 5 times the dose or 4 times the dose for a coleopteran pest. And for termite management, we are discussing about that imidacloprid formulation, Termex and Premise. It is recommended at the rate of 2.5 ml per liter, not 0.3 ml per liter or 0.25 ml per liter. It's the usual concentration of an OP, carbamate or an organochlorine, 2.5 ml per liter. One thing Bindu told in the first instant itself was it a new generation insecticide, we use it at lower dose. But at that lower dose, it won't have any effect against termites. If you want to use it as a termiticide, we have to use it at a higher dose. We are using it as a higher dose at 2.5 ml per liter, and that formulation is 30.5 SC. The other SL formulation which we normally use against crop pest, it is 17.8 SL. So that means almost half the concentration. That formulation that we use is half the concentration. We are increasing the concentration of the formulation which we are using for termite management. Again, we are increasing the dose of the molecule because the number of receptors are maybe low in those molecule in those group of insects. If the number of nicotinic acetylcholine receptors which have affinity to neonicotinoids or imidacloprid is low in a particular group of insect, we have to increase the dose to target almost all the nicotinic acetylcholine receptors. That's what we are seeing. For those insects which are having more number of receptors, such as aphids, more number of receptors which have affinity to imidacloprid, we may need only very little quantity of the insecticide because there are n number of receptors. A very small quantity is enough to bind to receptors and lead to the mortality of the insect. Now we understood how imidacloprid sensitivity varies with different species of the same group of insects. Okay, this is the next part. This is with respect to almost all the neonicotinoid molecules, imidacloprid, clothianidin, thiamethoxam, dinotefuran. If you see any paper with respect to neonicotinoids, this abbreviation is universal. Imidacloprid is IMI, clothianidin is CLO, thiamethoxam is TMX. So this is the common abbreviations we use. And now we have sulfoxaflor and fluopyradiferon. Again, if you see rank mode of action classification, this is given in another subgroup because of the slight difference in the structure, but both act on nicotinic acetylcholine receptor. Here you have nicotine. See the mammalian toxicity here, this table. The mammalian toxicity of nicotine is LD50 is 50 to 60 milligram per kg, extremely toxic. But take the case of neonicotinoids, most of them are above 1000 milligram per kg, LD50. See the difference. Nicotine, it is extremely toxic, whereas the molecules which are designed based on the structure of nicotine is very low mammalian toxicity. Then from now onwards, we will be discussing how neonicotinoids have low mammalian toxicity and how it is more selective towards insect and not to mammals. That we'll be discussing now. So here I have shown, here it is nicotine, here it is neonicotinoids. What I have seeing here is nicotinic acetylcholine receptor. So this is the nicotinic acetylcholine receptor, and see this is nicotine, this is neonicotinoid. So here both nitrogen will be having positively charged, so it will interact with the negatively charged amino acid in this receptor, and this will interact with this nitrogen of nicotine will interact with the cytosine, and oxygen of neonicotinoid will interact with hydrogen. So that's the point. One thing you should remember is that here the nitrogen is fully positively charged. That's what you can see, plus. But here the nitrogen is delta plus. That means it is partially positively charged. Neonicotinoid. All the neonicotinoids are not that fully charged. It is partially charged, partially protonated. We call it as partially protonated. And see the distance between the receptor sites of nicotinic acetylcholine receptor. This 5.9 angstrom. Both nicotine, the atoms which bind to the receptors, these two nitrogen atoms, the distance between these two nitrogen atoms is the same 5.9 angstrom, and that atoms which bind to these receptors is in neonicotinoids also the distance is the same 5.9 angstrom. That means Nicotinic acetylcholine receptor, the distance between the receptor sites and the distance between the sites of binding to either nicotine or neonicotinoid, both are same 5.9 angstrom. So that means both nicotine and neonicotinoid can bind perfectly to nicotinic acetylcholine receptor because the distance is the same 5.9 angstrom. The distance between the receptor sites and nicotinic acetylcholine receptors is 5.9. In both nicotine and neonicotinoids also it is 5.9 angstrom. So well fine. Then how come it differs? Here, this is one thing I told you, it is partially protonated. This partial protonation of partial positive charge of neonicotinoids is because of the electron withdrawing oxygen. Oxygen is high electron negative, it's, or electron withdrawing molecule, electron withdrawing atom. So, because of the electron withdrawing nature of oxygen, this nitrogen will get a partial positive charge. This positive charge is extremely essential for interacting with this negatively tipped receptor site of nicotinic acetylcholine receptors. Positive charge is essential. So in neonicotinoid, this is given by this positive charge is given by this electron withdrawing oxygen atom. Okay. These things, it is well explained in the papers I have uploaded in Moodle. Go through it. So this is what happens in an insect. This is nicotine, this is imidacloprid, this is cuticle, this is the ion barrier. See nicotine. Nicotine is a contact person. It can easily pass through cuticle. See the arrow over here. This is a bold arrow. That means nicotine can easily pass through cuticle. But neonicotinoid, imidacloprid, the ability of imidacloprid to pass through cuticle is very low. That's why we have given dashed arrow, broken arrow. It has to be ingested. That's why sucking pests suck imidacloprid from the phloem. It is all the neonicotinoids, systemic molecules absorbed into the plant system, transmitted through the phloem. When the aphids or any sucking pest suck sap from the phloem, it gets ingested into the body. So it's not actually entering the body through the cuticle, it is entering into the body through the digestive system. So imidacloprid reaches the system primarily through because of the systemic nature of this insecticide. Is it clear till now? Okay. So once it is here, it has to cross the ion barrier to reach the nicotinic acetylcholine receptors located in the central nervous system. But one thing happens over here. A fully protonated, a fully charged molecule cannot cross ion barrier because these ion barriers uh, respond to ionic. So these are respond to positively charged atoms, negatively charged atoms. That's why it responds to sodium, potassium, chloride, calcium, etc. So a fully charged nicotine cannot cross this ion barrier efficiently. So again, you can see it is broken arrow. Whereas neonicotinoids, imidacloprid, it is partially protonated. Slight positive charge only is there. So it can effectively pass through this ion barrier and reach the central nervous system and interact with the nicotinic acetylcholine receptors in the central nervous system. Understood? We have seen it is partially protonated, neonicotinoid. This partial protonation permits the movement of neonicotinoids from the body into the central nervous system. But nicotine is fully protonated, fully charged. These fully charged molecules cannot pass through this ion barrier. That is one thing. Well, let's see how this selectivity occurs. That's what we discussed. LD50 is nicotine is highly toxic andro that we have seen, and that distance is 5.9 Armstrong. The receptors is also having 5 point distance of 5.9 Armstrong. That's also we have seen. But neonicotinoids and nicotine have different protonation states. Nicotine is cationic and selective for mammalian nicotinic acetylcholine receptors, while neonicotinoids is not protonated. Actually, we can say it is still protonated, partially charged, and selective for nicotinic receptors. This partial charge, partial positive charge, or partial protonation is given by the electron withdrawing nitro or cyano group. This isotope in that oxygen atom withdraws electron. And this partial positive, even a partial positive charge is sufficient for interaction with insert nicotinic acetylcholine receptor. But a full positive charge, fully protonated molecules can only interact with vertebrate nicotinic acetylcholine receptor. That is one way of selectivity. I will repeat. Insect nicotinic acetylcholine receptors can interact with molecules those even have those with partial protonation. That's why a partially protonated imidacloprid can interact effectively with nicotinic acetylcholine receptors in insects. Whereas in mammals, a fully protonated molecule is needed for its binding with nicotinic acetylcholine receptor. So, a fully protonated nicotine binds to mammalian nicotinic acetylcholine receptors, where a partially protonated imidacloprid or any other neonicotinoid fails to bind to nicotinic acetylcholine receptor. Clear? And another way of achieving selectivity is in insects, nicotinic acetylcholine receptors is present only in central nervous system. So, the neonicotinoids cross the ion barrier and reaches the central nervous system to act on nicotinic acetylcholine receptor. So, the partially protonated one can easily cross the central nervous system. But nicotine, which is fully ionized, which has only limited access to central nervous system. That's why even though nicotine we consider as a very botanical insecticides, its efficacy is low. Have you ever used a tobacco decoction for the management of any sucking pest? If you have used it, you will find its results are not good compared to neem, another botanical. Neem is more effective to nicotine. One thing is nicotine is extremely unstable in the environment. That is one thing. But another thing is that this nicotine cannot cross this ion barrier and reach the central nervous system, where the majority of nicotinic acetylcholine receptors are located in the case of insects. Whereas in the case of mammals or vertebrates, nicotinic acetylcholine receptors are present both in the central nervous system and peripheral nervous system. That's why nicotine is toxic to vertebrates or mammals, because nicotinic acetylcholine receptors are present in peripheral nervous system also. In insects, it is located mainly in the central nervous system. So nicotine cannot cross ion barrier and reaches the central nervous system, whereas nicotine, which can reach the peripheral nervous system, and for vertebrates where the nicotinic acetylcholine receptors are located in the peripheral nervous system, it is toxic. Clear? And neonicotinoids, low binding affinity to vertebrate nicotinic acetylcholine receptor. That's what I told, because of its partial positive charge. And another difference, that is in one of two papers they have referred it. They have found out that both nicotine and neonicotinoids interact with different sites of nicotinic acetylcholine receptors. That they do not bind to the same sites in the nicotinic acetylcholine receptors. They bind with different sites in nicotinic acetylcholine. That's what I told in the last 2 points. And as that is slightly different from what I discussed till now, because that is a recent advance. Ionized nicotine binds at an anionic subsite in an mammalian nicotinic acetylcholine receptors, whereas neonicotinoids binds with the unique subsite of cationic amino acid residues in insect nicotinic acetylcholine receptor. That means the binding site itself is different in the case of insects and mammals. So that is one thing certain scientists are arguing. So whatever it may be, one thing is that both structure-wise, both the molecules remains the same. The distance 5.9 angstrom. Both are protonated, but that protonation differs slightly. One is fully protonated, the other one is partially protonated. So this partially protonation made for binding with insect nicotinic acetylcholine receptors, whereas full protonation is needed for binding to vertical nicotinic receptors. Another thing is that the nicotinic acetylcholine receptors are located in the case of peripheral nervous system in the case of vertebrates. So nicotine, which can't cross the ion barrier, can interact with nicotinic acetylcholine receptors located in the peripheral nervous system itself. But in the case of insect, nicotinic acetylcholine receptors are located in the central nervous system. But a fully protonated nicotine cannot pass through this ion barrier and reach the nicotinic acetylcholine receptors, whereas a partially positively charged, partially protonated neonicotinoid can pass through this ion barrier and reach the nicotinic acetylcholine receptor sites. And of late, there are few papers which is published from 2017 onwards. I have seen a few of it, which argue that there are certain receptors in mammals also which can to which neonicotinoids can bind, but that binding affinity varies with the different neonicotinoids. It's not the same. So certain scientists argue that the mammalian there is a bit of mammalian toxicity to neonicotinoids also, but it varies with the neonicotinoid molecules. Imidacloprid, thiamethoxam all differs in their binding affinity. So that's a recent advance over what we have studied. Let's see how scientists come up with more and more explanations with it. So this is the same picture, which this is the different side I have discussed. Scientists argue that this paper I have given to you, insect nicotinic acetylcholine receptor and mammalian nicotinic acetylcholine receptor, they bind to different sites. One is positively charged, one is negatively charged. That is one opinion of another set of scientists. And with one more slide, I will finish off today's class. We have two groups of insecticides acting on nicotinic acetylcholine receptors. One is imidacloprid, another one is spinosins. Both act on nicotinic acetylcholine receptors. This neonicotinoids are nicotinic acetylcholine receptor competitive modulators. That means it competes with acetylcholine and binds to nicotinic acetylcholine receptors. Spinosins are nicotinic acetylcholine receptor allosteric modulator. That means it binds to a site different from the binding site of acetylcholine. So let's see the binding sites. See, I will show this here. Okay. See, this is the nicotinic acetylcholine receptor. And you can see this is the binding site of acetylcholine. At the same location itself, neonicotinoids bind. So that's why we call it as a competitive modulation. Whereas see, spinosine, it is an allosteric modulation. It doesn't bind to the site of binding of acetylcholine. It binds to another site of nicotinic acetylcholine receptor. And it modulates the activity. It closes and opens the nicotinic acetylcholine receptor. Understood? Any doubt?
സർ അയണൈസ്ഡ് എന്ന് പറയുന്നില്ലേ
ആ
അത് പ്രോട്ടോണേറ്റഡ് തന്നെയല്ലേ അർത്ഥം മീൻസ്
അതെ
എനി
അതെ
ചാർജ്.
പ്രോട്ടോണേറ്റ് ചാർജ്. I took imidacloprid because literature is giving a better clarity with respect to neonicotinoids for discussing about selectivity. For other groups, if you start discussing it, it's not that clear. Here, slight, slightly better scientists have evolved the selectivity of it. Now, in today's class, we have seen how an insecticide which is acting on nicotinic acetylcholine receptor becomes toxic to one group of insect and non-toxic to another group of insect. That's depending upon the kind of receptor, the number of receptors on the sensitivity of the receptors. It can vary with different species. And then we have seen how a particular insecticide becomes selective to insects and non-selective to mammals. Okay, is it fine? Thank you. Hope all of you are fine.
Yes, sir.
Stay safe. Don't venture outside. The situation is not that